Hello.
Hello, sir.
Good morning, sir.
Sir,
Good morning, madam.
Good morning. Okay.
shall we start, sir?
Over to Grish, madam.
Shall we start, sir? Sir, shall we start, sir? Right. Dignitaries,
We can start.
so dignitaries, coordinators of the program, this FTP program, participants and my colleagues, a very good morning to you all. And I cordially invite you to the fourth day of FTP program. And today we have our honorable chief guest and the session chair, Professor N. Balaji Garu. So before starting this session, I would take the privilege of introducing Professor N. Balaji Garu to the gathering. Dr. N. Balaji Garu obtained his BE degree in Electronics and Communication Engineering from Andhra University in 1996. He received his master's and PhD degree in Electronics and Communication Engineering from Osmania University, Hyderabad. He worked as a professor and HOD of the Department of Electronics and Communication Engineering of JNTUK, University College of Engineering, Vijayanagaram. Also, he worked as HOD of EC Department and Vice Principal of UCEN, JNTUK, Narasaraopet during 2016 and 18. He worked as Director of Admissions, JNTUK, Kakinada from May 2019 to November 2019, Narasaraopet. Presently, he is working as Director Internal Quality Assurance and IQAC, JNTU, Kakinada. He is a Fellow of IITE, Life Member of ISTE, and also member of IEEE. Earlier, he worked as an executive member of AP Knowledge Mission, Andhra Pradesh State Government. He has executed more than 3 sponsored research projects, including successful delivery of product named Mobile Image Position and Performance Acquisition System. He is one of the principal investigators of Collaborative ITRA, which is Information Technology and Research Academy, a division of Ministry of IT and Communications sponsored project worth of 3 crores. He also executed AICT sponsored project titled Industry Institute Partnership Cell IIPC with an initial grant of 10 lakhs as a chief coordinator. He also got the sanction of 2 AICTE sponsored faculty development programs with a financial grant of 8 lakhs and also more drops with a financial grant of 9.5 lakhs. 3 patents of N. Balaji sir got published in Patent Official Journal. Out of 3 patents, 1 patent was awarded in 2021. He has guided both BTech and MTech projects in the areas of VLSI, radar signal processing, and embedded system. He has guided 3 PhD research scholars and 12 research scholars have been in the process. He has authored more than 60 research papers in national and international conferences and journals, and his areas of interest are VLSI, signal processing, radar, and embedded system. Sir, once again, we thank you for accepting our invitation, and I really take the pride of introducing you, sir, and I really thank for giving me the opportunity for introducing our eminent personality. Sir, thank you once again, and now you can start your session, sir. Thank you so much, sir.
Thank you, Grishma madam, for the nice introduction. Yeah, so today I am going to deliver the session on FPGA hardware co-simulation of image encryption using stream cipher based on chaotic maps. So the reason for this particular topic is that most of the research scholars, most of the academicians, they love to work in the area of image processing, and yeah, and they normally choose the MATLAB based implementation and so on. But the FPGA implementation gives a greater advantage. Let us look at what greater advantage we get by the hardware implementation. We will discuss in detail. Before going to this topic, actually this particular topic was taken as a research paper from Mr. Hassan and Amir on the research paper FPGA hardware co-simulation of image encryption using stream cipher based on chaotic map. We have taken this particular research paper and tried to implement the same on this one. So I found it somewhat good and useful for FPGA based implementation. So the contents of the presentation are like we'll discuss the problem statement, then we will discuss what are the objectives of this particular topic, then abstract and introduction of this particular topic. What is fixed point chaotic map based on pseudo random bit generation, and finally we will see the FPGA platform for image encryption and what are the different random test results and what is the performance of the implemented system and its security analysis can be done, and a hardware co-simulation of image encryption based on FPCM. This is also we are going to discuss, and finally we'll conclude this. So before going to this topic, in view of the what we will be sending a lot of data over the internet. So in view of the increasing risks over the internet, there is a need to encrypt the data. We are all aware that we want to either for any defense application or our personal data. So they are more prone to hacking and then unauthorized parties attacking, and then theft of data is a big problem. So in view of the increasing risk for the internet, there is a definite need to encrypt the data to avoid attacks from unauthorized generate a key based on the plain text image rather than single key for any plain text image, so that we want to increase the security level to a higher extent. And if the key is generated from the plain text message, the crypt analysis can be more difficult. And this method can be implemented by using a technique called chaotic maps. We will discuss what is meant by chaotic maps and why we are going for this particular chaotic maps in due course presentation. So I think you might have understood the need for encryption of the data. So what are the objectives of this particular project is we will encrypt an image using chaotic cryptographic techniques, and we will implement it on FPGA using a tool called Xilinx system generator. That's what the main project object. So more specifically, in this project, to develop a model of image encryption system using chaotic maps. The chaotic maps, there are different kinds of chaotic maps. They are like logistic maps, lossy map is there, tent maps. So these are the three different kinds of chaotic maps which are considered by the authors in this particular project implementation. And there are two hybrid systems that the authors have implemented. The two hybrid systems are Cascade and XOR chaotic map systems. By combining the three basic maps. The three basic chaotic maps are mentioned above: logistic, lossy, and tent maps. And to implement the model on FPGA platform using Xilinx system generator, also the performance and security analysis of this implemented model is analyzed to analyze the encryption standards. These are what the objectives of this particular project. Coming to the abstract of this particular project, the authors has tried to develop a new model of image encryption system using stream cipher based on fixed point chaotic maps, which are designed using Xilinx system generator in an efficient way. Two pseudo random bit generators depends on chaotic maps are proposed. The two pseudo random bit generators that are proposed are fixed point XR chaotic maps. PRBG corresponds to pseudo random bit generator. So FP, shortly abbreviated as FPXR CM, and PRBG, which is the short form for fixed point XR chaotic map, and fixed point cascade chaotic map, the short form of which is FPCCM PRBG. So the randomness in tests in the National Institute of Standards and Technology are used to test the randomness measures of the proposed PRBGs. So in any encryption, first of all, if any unauthorized party want to hack the data, there should be a complex one, and the randomness will help us because whatever is that randomly generated cannot be easily decrypted by the unauthorized parties, so that the data will have more and more security. The security analysis also, like histogram, correlation quotient, information entropy, differential attacks, these are used to analyze the efficiency of the proposed system by the authors with due acknowledgement to the authors. Also, the implementation was done on a Xilinx FPGA. The result that they had proved these particular chaotic maps are suitable for image encryption based on stream cipher and outperform the existing encryption algorithms. That's what we can understand from this one. Now, the question is, normally all image encryption, there exist a lot of image encryption implementations, and these can be simply done on MATLAB. But why should I go for FPGA implementation? Why should I go for hardware implementation? So any, not only this image encryption, any of the implementations, we can do it making use of a MATLAB software, and then just we can stop with that. Why should I go for either FPGA implementation or VLSI based implementation, ASIC implementation, or maybe a platform maybe use that is another hardware, or you can use a advanced microcontroller implementation. So now the question comes, why should I go for these hardware implementation? So here is the comparison between the software and hardware implementation. The software implementation is sequential in nature. So what is meant by sequential? The software implementation gets executed in a sequential manner after the first instruction, then second instruction, then third, and so on. As a result, the sequential implementation is time consuming. Whereas in hardware implementation, it is concurrent in nature. So you may be able to execute the instructions in a concurrent manner, like that is in a parallel manner. The instruction 1, 2, 3, and so on, they gets executed in a parallel manner, so that there will be a faster execution in case of hardware implementation. When it comes to the software implementation, it's more prone to error. Software implementations are, whereas hardware implementations, they are robust in nature, and you can overcome the limitations that are there in the software implementation. The software implementations, they need programming skills, whereas the hardware implementation needs the design skills. When it comes to the software implementation, it is of low cost when compared with the hardware implementation. When it comes to the hardware implementation, there will be increase in the cost, a significant increase in the cost. The reason being that you need to buy the hardware like sensors or peripherals which need to be interfaced, the powerful processor based board also you need to buy. So there is a significant increase in the cost of the hardware. So hardware implementation is generally of higher cost. When it comes to the software implementation, already well developed programming methods are there. You have number of programming methods, programming languages support like C, C++, V, C++, Java, so MATLAB. You have wide variety of programming methods are there. But when it comes to the hardware prototypes, they are hard to build. They require definitely some um, um, design skills. So now the running speed of software implementation is computationally costly and time consuming. So the software systems may not be sufficient and satisfactory when real time is needed. And therefore, on chip hardware implementation is necessary for real time applications. Nowadays, hardware and software implementations, they are commonly used in different fields of application. You may see that most of the applications has a combination of hardware and software. The combination of hardware and software is called a firmware. Am I right or not? Although the amount of software implementation, it is widely prevalent, there is an integrated implementation methodology that combines both hybrid software and hardware approaches. The hybrid approaches, they will benefit from software learning capabilities in the aim to attain efficient real-time hardware, like for example, FPGA, field programmable gate array circuit implementation. And for instance, most systems are developed and implemented in software when the particular task does not require as much speed. You may go for software implementation. And the hardware implementation is necessary for time consuming application. The most important limitation is to respect the real. Now let us look at what is meant by a real-time system. Real-time, we are talking about real-time constraint. So far what we have discussed is why should we go for hardware implementation and why should we go for particularly FPGA implementation. Now let us look at what are real-time systems. The real-time system, the execution in real-time system, the execution of applications is with time constraints. Again, you can divide your real-time systems into two types: hard real-time systems and soft real-time systems. And when it comes to the hard real-time system, take an example of digital fly-by-wire control system of an aircraft. So in a digital control system of an aircraft, no delay will be accepted because the lives of the people, the whoever the passengers traveling in the aircraft, they depend on correct working of the control system of the aircraft. Any delay will lead to the catastrophic effect and loss of lives of many passengers who are traveling in the aircraft. So, in such cases, no time delay will be accepted. They are called hard real-time systems. And when it comes to the soft real-time systems, they accept lower performance for delay. It is not catastrophic. When deadlines are not met, it will take longer time to handle one client with the vending machine. For example, for soft real-time system, in most of the airports, you will see a soft drink vending machine. If you deposit the required amount, the soft drink gets dispensed. The soft drink gets dispensed. So even there is a few minutes or few seconds delay, there won't be any catastrophic effect. There won't be any loss of life and other problems. That kind of systems are called soft real-time systems. One more example for hard real-time system is like your pacemaker. Generally, the heart patients will be using the pacemaker for if they are suffering with improper heartbeats, then they will be using a pacemaker for that. So any delay will lead to the loss of life of that heart patient if the pacemaker doesn't function properly and doesn't meet the timing constraint. That will result in the loss of life of the person. So that is one example. And you may use some dedicated circuits like application specific integrated circuits for implementing these kinds of real-time systems. So that's what the use of this. And field programmable gate array implementation is particularly chosen as it is the field programmable gate array implementation has the greater advantage of that the FPGAs are reconfigurable and as well as reprogrammable. For example, if I want to program my FPGA as a counter, so erase whatever the basically FPGAs are like EPROM, erasable, programmable, read-only memory based. So you may erase the previous functionality and you may implement the new functionality. That's what the greater advantage that you get with FPGA implementations. So this gives, I think, a clear justification why we are going for hardware implementation, why we are going for FPGA implementation. We got a clear idea why we are going for this kind of implementation when sophisticated software implementations are there, why we are talking about VLSI implementation or FPGA implementation. I think this has a good justification why we are going for FPGA implementation. Let us look at into the topic. Uh, so in the few years, the communication technologies like mobiles and internet works, they have rapidly evolved, and the domain of information transmission is extended. However, this area presents new challenges for saving and exchanging multimedia messages. Like multimedia message, you are aware of that having image, audio, or video from unauthorized eavesdrop when transmitted. Therefore, to make a transmission more secure over the internet, the multimedia messages such as images and videos must have encrypted to avoid attacks from unauthorized parties. In the beginning itself, in the problem statement itself, we have clearly discussed that whatever the data transmission we want to do in order to have a secure data transmission, we'll try to encrypt the data. That's what the main concept. So earlier, different techniques were proposed to transmit data securely and also to identify the important levels of security depending on the purpose of the communication. And traditional encryption types have lower efficient in securing images by using encryption systems, and they have some drawbacks or weakness in high stream data encryption. So to make the transmission of data over the internet more and more secure, encryption of images must be designed in an efficient way with low complexity and as well as high security. And the use of chaotic maps in cryptography to encrypt images has emerged. It emerged as a potential solution for many security problems because chaotic maps have many advantages for random characteristics like sensitive dependence on initial conditions and also parameter values. We will discuss what is meant by this sensitive dependency on initial conditions in the due course of the presentation. Parameter values. So what are the different parameters that we are considering? Simple design and has an aperiodic signal, which make it suitable choice for cryptography systems. In the previous years, researchers has developed many image encryption algorithms. These algorithms have been designed using chaotic system technique to encrypt images. Because of chaotic systems have many sensitive properties and show better performance than traditional encryption techniques like DES and AES, which are the standards for encryption techniques. Many researchers aim to implement an encryption model to encrypt images with chaotic maps. And we have been repeatedly saying chaotic maps. So let us try to understand what is a chaotic map. So a chaotic map is a map. It's nothing but an evaluation function that exhibit some sort of chaotic behavior. So let us try to understand what is chaos. The chaos refer to apparently random states of disorder and irregularities that are actually governed by underlying pattern and deterministic laws that are highly sensitive to initial conditions. So actually why we are going for this chaotic maps are we want to create randomness so that nobody can predict our key. Nobody can be able to decrypt our data, whether it is image data, video data, or whatever it may be. So we want to create a more and more complex random key in order to secure our data. And the following are the properties of chaos behavior. What are the properties of chaos behavior are? The first one is it must be sensitive to initial conditions. So what is meant by sensitivity to initial conditions is sensitive to initial condition means that each point in chaotic system is arbitrarily closely approximated by other points that have significantly different future paths or trajectories. Thus, an arbitrary small change or perturbation of current trajectory may lead to significantly different future behavior. This means that we want to have a completely different future behavior by choosing chaos because they are sensitive to initial conditions. When sensitive to initial conditions, each point in chaotic map is arbitrarily closely approximated by other points, which have significantly different future paths or trajectories. And also, one more important property of chaos is it must exhibit non-periodicity. Now the question comes: why this property was highlighted? Why we are saying it must exhibit non-periodicity? For example, you are transmitting a data 1010. So after 1010, what is the next sequence? What is the next sequence? Is again 10. So how you are able to predict and tell about this is it is periodic in nature. So the periodic signals, these are very to hack and easy to predict. Okay, but whereas the chaos behavior, we are saying it must exhibit non-periodicity. So now the non-periodic signals, they are quite difficult to predict and quite difficult to be hacked easily. So this is what this is the reason why we have chosen this chaotic map. because under the properties of chaos, we have the non-periodicity is one property, and the other important property that we got is sensitivity to initial conditions. So these makes your for this encryption. And as we said earlier, there are different kinds of chaotic map: fixed point chaotic map, and based on pseudo random bit generation. So for fixed point chaotic map, you have shows general structure of fixed point chaotic map based on pseudo random. In the first case, the initial values are taken as naught. So let's take the figure. In the figure, you can, is the figure visible to you? Figure 1. General structure of FPCM PRBG. So in the figure, you can observe there are two n-bit registers. You can observe that there are two n-bit registers for which, for the first n-bit register, the initial value, the initial values are taken as x0 and y0. In the first, the initial value x0 and y0 with the n bits are derived into the digitization functions. Xn plus 1 is a function of xn comma yn, and similarly yn plus 1 is a function of xn and yn. So yn plus 1 is equal to, as it is a function of xn and yn, g of xn and yn, where xn plus 1 and yn plus 1 are the next state values. So you observe that the next state values are dependent on the xn and yn values. Next states are dependent on the xn and yn values. The sample of xn is finite precision format with the n-bit length. And bj belongs to values of 0, 1, 2 bits in between 0. The fixed point format is designed with word length. WL corresponds to word length of 32 bits. That is found to be the best choice to obtain a chaotic signal. The n bits are then passed through a function called slicing function. You can observe the same thing in the figure. There are n-bit register and fixed point format is shown. There is a block called slicing function. Observe that these are passed through a slicing function, and the output of the slicing function is passed through a parallel to serial converter. And finally, you are able to get the fixed point observe in the figure 1 block diagram of FPCM PRBG. What is FPCM PRBG is fixed point chaotic map pseudo random bit generator. So the n bits then passes through a slicing function to select m, which is the least significant 8 bits, and converting it into serial bits using parallel to serial converter. So that's what we have just now seen in the block diagram. The output of the slicing function is given to a parallel to serial converter to get the serial bits. Here the m bits which are selected, they are here m is equal to 8 bits, that is suitable to synchronize with the plane image. And you have the second figure. We said that slicing function. So what is inside the slicing function is clearly shown in figure 2. The slicing function inputs to the slice are most significant bits and least significant bits, MSB and LSB. That means the entire bits are given as the input for slice. and the output of the slice you can observe is a LSB bits. Least significant bits are the output. Two, that is showing the slicing function. The purpose of select the least significant bit is high randomness bits are. See, now the question comes, why we are particularly interested in slicing function? The reason is that the least significant bits, they are high randomness bits are existing in these bits compared with the MSB bits. So actually we want high randomness. Why high randomness? We just discussed that the more the randomness, more is the predictability and more is the security for us, so that it won't be hacked by unauthorized parties. That's what our intention. Hence, we prefer more and more randomness. That more randomness is there in least significant bits rather than in most significant bits. And hence, we do prefer the output of the slice function as LSBs rather than MSBs. This is the reason. So in this section, different pseudo random generators based on chaotic maps like logistic and logi and tent maps. We said that we will be using three mapping functions. So the three mapping functions we will discuss in detail. The reason of selection of these maps is the simplicity. Why you have chosen logistic, logi, nature, and they are efficient in performance in image encryption. This is the reason why there exist many chaotic maps. Why particularly these three chaotic maps is, it was found that these three chaotic maps are simple, and also they have high efficiency in image encryption. Now, as we said that we are going to use three chaotic maps. The first chaotic map that is used is the chaotic logistic map. The simple mathematical equation for this chaotic logistic map is given by xn plus 1 is equal to r into xn that gets multiplied with xn minus 1. This is what the first chaotic logic map. The interest values of parameters are those in the interval 0 to 4, where xn is the state variable, and that lies between 0 and 1. XSG, wherever you find XSG, you need to understand that it is a Xiling system generator. This is a tool that is used to implement a Xiling system block diagram. Okay, if I want to implement any application, okay, or any function or anything on the FPGA, so I should have a design entry. The design entries that are allowed are, I have to write a hardware description language. The hardware description language, two types are there. One is you are aware of it, VHDL. Another one is Verilog. VHDL is very high speed integrated circuit hardware description language, and Verilog is another hardware description language. So either I should have an expertise in writing the HDL codes. So I am not an expertise in HDL coding, but I'm much acquainted with MATLAB and as well as block diagram level entries. In that case, the preferred tool is Xiling system generator. My time bound is very less, and I don't have any expertise in HDL programming languages. Then go for a MATLAB Simulink based implementation, where the MATLAB Simulink has a link to the Xilinx FPGA platform, that is a Xilinx system generator tool. So what are the requirements for working with this Xilinx system generator tool is you must have a licensed MATLAB simulating full featured MATLAB software should be there, and Xilinx ISC version compatible with MATLAB version. Compatible means Xilinx system generator tool will work with compatible MATLAB and Xilinx ISC integrated software environment or integrated simulation environment. So now Xilinx ISC has become outdated. Now Xilinx has renamed it as Xilinx Vivado, and Vivado is the latest Xilinx ISC software that is being offered by the company named as Xilinx, and this is being widely used in FPGA programming. So pre-requirements for the implementation are that you must have a MATLAB software pre-installed in your system, and also Xilinx ISC or Vivado compatible with that MATLAB software must get installed in your laptop or a desktop system. These are the requirements for the implementation of this particular project. So Xilinx system generator you may use for implementing the equation one. So as I told you, the Xilinx system generator tool is quite easy. Like it's like a block diagram level entry. So I want a particular a block. So I may just need to draw drag and drop. In the library, I have the tools like I have a encoder block. There is a communication block set. So the communication block set requires an encoder or decoder or a transmitter receiver. So these particular blocks are readily available. Just I can select those blocks, drag and drop, and then connect and get the required functionality. That's what the advantage that I get from this Xilinx system generator or Simulink blocks. So I can comfortably implement a good number of applications making use of this Xilinx system generator. So the equation can also not write a code for xn plus 1 is equal to r into xn multiplied with 1 minus xn. Simply I can implement even this equation using Xilinx generator to produce fixed point logistic map pseudo random bit generator. The parameter of fixed point representation for these maps are integer length is equal to 2 bits and the fractional length is equal to 30 bits. And the value of R is chosen as 4 in the chaotic logistic map. Another chaotic map is chaotic lossy map. You observe that what is the variation between the previous chaotic map and this chaotic map is the difference between chaotic logistic map and chaotic logic map is that the function, the mapping function is going to change. Earlier, the mapping function is xn is equal to r into xn into 1 minus xn. Whereas here, the two-dimensional mapping function that is given as xn plus 1 is equal to 1 minus alpha xn plus yn. And yn plus 1 is equal to beta into xn. And alpha betas they are the control parameters of this logi map, and xn is a state variable. And similarly, you can make use of Xilinx system generator to implement this. See, if at all, if I am doing a software implementation, what do? I will just write a code for this equation. Which equation? Xn plus 1 is equal to 1 minus alpha mod xn plus yn. But I am not writing a code, just I want to do it as a Xilinx system generator block. So all the logic maps, all the chaotic maps as simply with the block diagram level entry, making use of Xilinx system generator. And we will apply to the system to produce fixed point lossy map pseudo random bit generation. The parameters of fixed point representation for this image are integer length 4 and fractional length of 28 bits. And you may choose the values of alpha and beta as 1.4 and beta is equal to 0.3. The authors has taken the values of these control parameters as 1.4 and beta as 0.3 after number of iterations, and they found that these are good for getting good randomness and good security. And another chaotic map, the last chaotic map is chaotic tent map. As I told you that between one chaotic map and the other chaotic map, the mapping function is going to change. Here again, the mapping function got changed. In mathematics, the tent map is an integrated function in the form of a tent forming a discrete time dynamic systems. It takes a point xn on the real line and maps it to another point as written in equation 3. This is equation 3 is given as xn plus 1 is equal to mu into xn. When it is mu into xn is for xn less than half, and it is mu into 1 minus xn for half less than xn. So when xn is less than half and when xn is greater than half, the equations of the mapping function is going to change, where this in this one where mu is a positive real constant. I think we had lost that mu is a positive real constant, and here that mu is equal to 0.5, and xn is the state variable. Depending on the value of mu, the tent map demonstrate a range of dynamic behavior ranging from predictable to chaotic, and Xilinx system generator is can be used to implement the equation 3. The parameters of fixed point representation for this map are you can have the integer length as 4 bits and the fractional length as 28 bits. So finally, what is the use and purpose of all the 3 chaotic maps? You observe that we give all the 3 chaotic maps as the input for an XOR gate, and finally we are able to get a K. So a fixed point XOR chaotic map was proposed by author. In this system, as with the 3 chaotic map, logistic map, lossy map, tent maps, they are combined together using the XOR function, which is shown in figure 3. You can see in figure 3 that 3 chaotic maps, they are combined and they are given to given as the input for the XOR gate. In the figure, the 3 pseudo random bit generators, FPLOM, PRBG, FPLM, PRBG, FPTM, PRBG, they are XOR to generate the new version. Okay, so which are fixed point XOR chaotic map, PRBG. Okay, and all these are combined. They are combined or XOR to generate a new version of the random bit generator. So you got a random bit generator, and another new version is fixed point cascade chaotic map based PRBG. You observe we are cascading. What we are cascading is we are cascading. Earlier, all the 3 are given as the input for XOR, but now output of FPLOM is applied as the input for FPLM, and output of FPLM is applied as the input for FPTM. So what are we doing is we are cascading. So we are cascading the 3. What are the 3? Logistic map, fixed point logistic map, fixed point lossy map, fixed point tent map. So you can observe that FPLOM corresponds to what? fixed point logistic map. FPLM corresponds to fixed point logi map. FPTM corresponds to fixed point tent map. Earlier, what we did, we have taken these three maps and given these three maps as the input for an XOR gate, and we got a random output. Whereas in the cascaded chaotic map, we are cascading the three mapping functions, three chaotic maps. The three chaotic maps are cascaded. You know what is meant by cascaded? Like input, output of the previous block is given as the next block, and output of the second block is given as the input for the next block. Then they are said to be, these blocks are said to be in cascade. So each chaotic maps are designed using Xilinx system generator with fixed point presentations, as mentioned before. And this figure shows the block diagram of fixed point cascade. What is meant by cascading? Just now we discussed output of the previous block is given as the input for the next block, and so on. They are called cascade. Cascade chaotic map based pseudo random bit generator. The output of the final map is passing through a function called slicing function, and then stream bits represent by FPCCM pseudo random bit generation is produced using parallel to serial converter. We discussed in detail about slicing function and parallel to serial conversion earlier. And we will take, as we said, that FPGA platform for image encryption. We have done a detailed discussion regarding why we have chosen FPGA platform image encryption. Why do we go for hardware implementation? Why do we go in hardware again, particularly for FPGA? We said that the FPGAs are reconfigurable, reprogrammable. So we get a lot of advantages with FPGA implementation. The general Xilinx system generator block diagram of the proposed image encryption is shown in figure 5. So this is what the figure 5. In this particular, this is a complete encryption system. Now, the question is, how do I implement this? Is, as I told you, what are the requirements for this one? What are the requirements for this particular one? Implementation. As I told you, that you must have a MATLAB software that got installed in your system, and as well as a what do you say, Xilinx Vivado or Xilinx ISC compatible version installed in your system. Now, let me share this Xilinx system generator. Yeah, what I will do is I will share new share. I'm going to show you
Sir, excuse me, sir.
Participants, can you see the screen sharing?
Yes, sir.
Yeah. So
Visible,
this
sir.
is what the environment that you can see. You can open a Simulink block. Okay, this gets installed in your system. Okay, so you may see on the desktop. You will, after installation, you will get. Now the desktop is visible to you, right?
Yes, sir.
Now on it, can you see a system generator
Yes, sir.
where I placed a cursor? So just click on that system generator. If you click on that system generator, it opens a MATLAB kind of environment, this one, and then as well as you will get a Simulink environment. Now let me show you that. Now again, I am going to share you that Simulink environment. Is the Simulink environment is visible to you? A block diagram level. So
Yes, sir.
you may just go for file. After you click new, you may open a blank model or model. Okay, so you observe that there is a there are libraries. Okay, you may search for any of the libraries. Okay, so you may just have communication system toolbox, and you have DS HDL coder. So you may just search for even system okay, audio system toolbox, feedback controller, signal processing. So you can create a Simulink model, a signal processing model, or whatever it may be. So just you can drag and drop these things. So for as I am doing an image processing application, what will be my input? Image encryption I am doing. Am I right? So my input must be an image from a file. So I am taking my input as okay. So just I'll take a block, and I can give the path for my file. A lena.jpg file is taken as the input for this. Okay, so just you give this lena.jpg as an image, and after giving the input, I need a the pre-processing block. Okay, so what this pre-processing block consists of, and why do we require this pre-processing? Okay, so is the screen visible to you? So they in the pre-processing, there is an input, there is a transpose, there is a conversion of 2D to dimensional, and there is a unbuffer. These are there. So let me explain what this pre-processing block will do. So I'm switching to again to the presentation. Just 1 minute. I'm going to share the PPT. There we are going to discuss about the pre-processing stage. So is the screen visible to you in the PPT? Pre-processing Simulink block. So the pre-processing Simulink block consists of a transpose block, reshape block, frame conversion, and unbuffer block. So why this pre-processing Simulink block is required is we have a grayscale image. Suppose a grayscale image in a 2D array size. Grayscale or color, whatever the image is in. Suppose we have a gray image in 2D array size as rows and columns. Am I right or not? Like 256 by 256, 512 by 512. So that means R and C, rows and columns, where R represent the row and C represent the column of an image. For Xilinx system generator implementation, the image must be converted into a 1D data array. Suppose because I want to implement on Xilinx FPGA, Xilinx system generator implementation, I need to do some kind of conversions. The image pre-processing block is used to convert a 2D image data into a one-dimensional data array. Because FPGA, as it is a hardware implementation, there is a need for conversion of this 2D image data into a one-dimensional data array. So the image pre-processing block, it includes the first block is transport, second block is conversion of 2D to 1D, and then frame conversion and unbuffer block. What the transpose block will do is it converts the rows into columns and columns into rows. So we have clearly mentioned the transpose block transposes the row to column and column to row, and convert to 2D to 1D block reshapes the column row matrix into a one-dimensional vector. Frame conversion block sets the output signal to frame-based data and provided to unbuffer block, which converts this frame to scalar samples output at a higher sampling rates. And buffer changes, of course, we have a pre-processing block and post-processing block. The reverse blocks we'll be using, like unbuffer is used in pre-processing, whereas buffer will be used in post-processing. And as usual, reshape and then transpose and data type conversion. So we'll discuss that unit 8 data also. What is that unit 8? So U means it is, we'll discuss unit 8. Okay. So I think now I will. Can you understand? Just I'm switching between the presentation and the MATLAB Simulink environment. Can you understand it? We have a pre-processing block here. Okay. So if I go to the original block, so pre-processing is an intermediate stage. I given this as input. So file, I can open this my original this thing. So here you can observe that there are three channels are there, 1, 2, 3. So basically the color has RGB. If at all, if my Lena image is say gray level image, I need not require the 3. Okay, but whereas if I am doing a color, then I require these three pre-processings and then transmitter, receiver. So all these are required. That's what you need to understand. Okay, so what you can observe. Now let us go back to our presentation. So so there is a pre-processing block, there is a gateway in, and you observe that there are XR maps. So for XR, so for XR there will be 3 logical maps that we are given as the inputs for the XR, and then output is given to the gateway out, then post processing. Okay, and then finally the video viewer. And The serial bits are obtained using parallel to serial conversion, as we discussed. In the decryption stage, the same pseudo-random bit generator key is used to recover the original stream bits that are passing through serial to parallel converter and back to MATLAB Simulink environment using gateway out. And we want to recover the plain image with the same size. Post-processing block is used to convert the serial sample to the original size, LR by LC, so row and column. And the figure 7 shows the post-processing block. This is the post-processing block we have already discussed, which contains the following MATLAB Simulink blocks: buffer, reshape, transpose, and unit 8 blocks. So unit 8 is a data type that is used for images. Okay. So the unit 8 U corresponds to unsigned, and int is integer. Okay. So that may so unit 8 is a data format, is widely used in image processing, particularly MATLAB implementations. We'll use that unit 8. And yeah, so as we discussed, we have to develop chaotic maps for the 3 mapping systems. The first map is FPLOM. What is FPLOM? Fixed point. What is FPLOM? We have taken 3 chaotic maps. Okay. What are the 3 maps? Do you remember or not? Logistic map. Am I right or not? FPLOM. FPLM is logi map. Then FPTM is tent map. So we are using we need to develop the block diagrams for all the 3. Do you understand or not? So for FPLOM development, this is what the block diagram, FPLOM system. So how do I develop FPLOM system is like, so a multiplexer is used. Why multiplexer is used? The nature of multiplexer is many to one, right? So it takes multiple inputs and gives a single output. And that is given to an adder subtractor, and then it is given to a multiplier and again a multiplier. Observe that this block diagram corresponds to the implementation of the equation for chaotic map. Okay, what is the chaotic map implementation? Xn is equal to R into Xn into 1 minus Xn. So this requires 2 multipliers. Am I right or not? What are the multipliers that require is there is a multiplication between Xn 1 minus Xn. Do you understand or not? So that multipliers are required. Fine. So you require a subtractor. Why you require a subtractor? 1 minus Xn. Am I right or not? For 1 minus Xn. Do you understand what we are discussing is that we have an equation for chaotic map. That equation is, can you see the screen? Xn plus 1 is equal to R into Xn multiplied with 1 minus Xn. In the equation, you can clearly observe that Xn is being subtracted from 1 minus Xn. So you need adder or subtractor, and Xn gets multiplied with 1 minus Xn. You require a multiplier. You require a constant. So that's the reason why you observe that there is a constant in the chaotic map implementation. And you need a delay element, Z inverse. So Z inverse is nothing but a delay element. You observe that appropriate constants are being used. X naught value. Observe that X naught The value shown is the initial value 0.93924 and so on. R value is clearly again given as 3.89. Observe, you are just taking the blocks from the Simulink block set environment, drag, drop, and then connect them, obtain the required functionality. That's it. It's a very easy way of doing it. But HDL coding for the same implementation of chaotic logistic map is a little bit difficult, because you need the HDL programming skills. The advantage here is, without having any HDL programming skills, you will be able to do this. See, and also, while if you are doing a HDL implementation, you need to take care about the floating point multiplication and all those things. Like, unlike MATLAB, in HDL, you don't have any built-in functions for floating point multiplication, because the HDL programming, it allows only the multiplication between the binary bits like ones and zeros, but it won't directly allow you to have the multiplication between the floating points and so on. Are you able to understand what I am explaining? Similarly, the second chaotic map, chaotic lossy map, will be implemented, and the chaotic lossy map has the equation xn plus 1 is equal to 1 minus alpha into alpha multiplied with mod of xn, modulus of xn plus yn. So for that, again, you require multiplier, you require a delay element, you require adder, subtractor. So all these. So you observe alpha value, beta values are clearly given. Beta, can you observe on the screen what is the value of beta? 0.3. What is the value of alpha? I am placing the cursor. Can you see that? Alpha value is 1.33. So we may use the appropriate alpha and beta values for obtaining the chaotic lossy map. Similarly, for chaotic tent map also we can implement. And finally, once we implement all the three chaotic maps, we may have the block diagram for fixed point XR chaotic map, pseudo random bit generator. So observe what is there in the diagram. The three chaotic maps are given as the inputs for the XR gate, and the output is fixed point XR chaotic map with pseudo random bit generation. And Xilinx system generator block diagram for FPCCM, pseudo random bit generation. And here this is a Xilinx system generator block diagram of a single pulse clock. We require a clock pulse also. Okay, so for obtaining clock pulse, we are using a register, a logical function of XR, and then a SR block, by means by which we are able to get a single pulse block. And after obtaining these things, now let us again go back to the implementation, and let us run and see what outputs we are going to get. So now, is the Simulink block is visible to you? Is the Simulink block is visible to you? Now, there is a green color button where I am placing my cursor. You get run. So once you develop all these, you need to integrate all these and then click on run. So it says compiling, and you are going to get on the screen the original image, then cipher image, and then decrypted image. So once your execution is over, on the screen you will get all the three images. Okay, so let me share images. I think the images are not visible to you. Visible on the screen. So you got the original image, you got the cipher image, you got the decrypted image. So these are the images, the input image, and then this cipher image and decrypted image. Now, fine. Now you want to test the standard of the your encryption. Like you said that we are using 3 chaotic maps, and then you are doing the XORing of these 3 chaotic maps and generating the randomness, and then you are okay having a highly secured encryption system. But there is a need for need for checking the effectiveness of your implemented system. So you require some parameters for checking the effectiveness of this particular system. So let us take those parameters. Okay, so I'll once again share my presentation here. I think the presentation is visible to you. So randomness test results. The National Institute of Standards and Technology are utilized to examine the randomness of proposed pseudo-random bit generators. There are 15 tests in NIST measures. Among all, the most popular test includes the frequency testing, block frequency testing, how many number of runs, rank, discrete Fourier transform, serial and cumulative sums, and autocorrelation tests. The generator random bits are successfully passing all the tests if the p-value is greater than or equal to 0.01 for all tests, where the p-value is the threshold value that is used to accept or reject the random bits. So what is p is nothing but a threshold value. These tests have better randomness if the p-value for a test is equal to 1. A p-value of 0 indicates that the sequence appears to be completely non-random. So if you are quite nearer to 0, more randomness, completely non-random. So the p-value of the randomness tests for FP XR, fixed point XR, okay, CMPR, PBRG, chaotic map, pseudo random bit generation, and FPC, CMPRBG, these are shown in table 1. So table 1, you observe the frequency, block frequency, run test, rank, DFT, serial, cumulative sums, and autocorrelation. So a group of UG students, BTech students, has implemented this particular project in the Python programming environment. This pseudo test, that is National Institute of Standard Tests, and for all the parameters, they did it using Python programming. So whatever you may use any of the programming language, they find somewhat difficulty in implementing using C programming language. They felt more comfortable Python programming language, and hence they did it using Python environment. Let me show you that randomness test, the tests that they implemented. So here you observe that mono all are showing pass and p-value as 0.475, and mono based test it has passed. Frequency within the block test, it is a pass. Run test is pass. There is a DFT test, and there is a serial test and cumulative sum test. The screen indicates that it has passed these tests. Okay, so you may go for again for the presentation to discuss the remaining things. So this is table 1. And you need a performance and security analysis. Different analyses are present to test the performance and security of the proposed algorithm, including histogram correlation coefficient, information entropy, key space, and differential attack analysis. So these are the performance parameters that were taken. What are the performance parameters? To test the performance of your encryption standard. So you have taken histogram, correlation coefficient, information entropy, key space, and differential attack analysis. The analysis in this section is applied for a different size of color images, and experiments are carried out. First one is the histogram analysis. So the histogram analysis represents the distribution of all pixel values. In general, the distribution pixels of the original plane image are very uneven, and some pixel values have high frequency in the plane image. Therefore, it is capable of exploitation. In order to resist the attacks, the encryption system should make a cipher image distributed as much as possible to prevent the cipher image to be attacked. So if I want to protect our data from the attacks, okay, the cipher image, the requirement is the encryption system should make the cipher image distributed as much as possible. So the original color image, as I have shown you, is a Lena image of size 256 by 256 is taken, and its histogram was done. Shows the histogram of, we have 3 channels for any color image. We have red, green, and blue channels of the original image, and we can see that figure. So the original is shown, and histogram of the red channel, histogram of the green channel, and histogram of the blue channel are shown. So you can see those histograms images of the red, green, and blue channels. The histogram of 3 RGB channels are also shown here. Just see these. So for histogram, you can use an online resource for running these, and then you can get the histograms of all the 3 channels. And now the parameters that we are taking are correlation coefficient. So let us define this correlation coefficient. The correlation coefficient analysis, it is widely used as a statistical measure between the original and ciphered image. An image encryption algorithm is said to be good. So this is one of the performance measure. See, I am saying the authors are saying that they have proposed a encryption algorithm by taking 3 chaotic maps and then chaotic maps, and then they have XOR'd that and generated a random, and then they found the algorithm to be very good. So how do I test my algorithm, my encryption algorithm is good? Is if it hides all the attributes of plain image, and encrypted image is totally random and highly uncorrelated. So there is no correlation between the original image and the cipher image. Then I am highly successful. The algorithm is highly successful. And the algorithm is more efficient because there is no correlation. But if there is a correlation, I failed in my encryption algorithm. Am I right or not? If the correlation coefficient is 1, then the 2 images are identical. See, if I see myself in a mirror, then the correlation coefficient is 1 because my image gets matched with the image in the mirror, right? So in this case, the encryption fails. So we are talking about the correlation coefficient, and the correlation coefficient is given by these equations. Okay, so the variance of x and covariance between x and y can be calculated making use of these equations so that we can get the correlation coefficient. And yeah, the correlation coefficients that are calculated for all the three types of chaotic maps are shown, and finally for the combination of the three chaotic maps, they are XORed, and then you observe that none of them has the value nearest to 1. That clearly indicates that the correlation coefficient value is quite nearer to -1, and that shows the encryption algorithm is good. Okay, this is what you can understand from this tabular form. Okay, so the image encryption using FPCCM is shown, a ciphered image is shown, and a histogram of the ciphered image red channel, and the histogram of ciphered image okay, and the correlation coefficient values clearly shows that now you can even make the correlation coefficient calculators for images of different sizes like 256 by 256, 512 by 512, 1024 by 1024 with different channels and chaotic map systems. You observe, so you are getting a quite okay, correlation coefficient value much closer to yeah, -1. That shows clearly that your algorithm is quite good. As the size is also increasing, that you are getting the correlation coefficient values also. Even for a 512 by 512 ciphered image, the tabular form gives a clear indication. So that's about correlation coefficient. Apart from correlation coefficient, you have another parameter called information entropy analysis. So how do we define this information entropy analysis? Entropy analysis, another security measure is the information entropy analysis that is often used to describe the uncertainty or randomness of an image. The information entropy of a signal is given by the equation sigma n is equal to 0 to 2 power n minus 1. P of Si is the symbol of probability. P corresponds to probability. Si is a symbol multiplied with a log function with base 2, and capital N is the bit number which represents the basic unit of source S, and 2n is all the combinations of the basic unit. and you have taken, let us take a Lena image of 256 by 256 and 1024 by 1024 respectively for different channels and chaotic map system. And there is a tabular form for information entropy analysis. So you will get these values. Okay. So almost for all the channels, you have got the same kind of information entropy. Okay, even the chaotic maps are doing well. Almost they're having the same values of information entropy that you can observe here from these tabular forms. The information entropy comparison of 512 by 512 image. So we have three tabular forms: 256 by 256, 512 by 512, and 1024 by 1024. Even these values are compared with the other existing. The authors has compared this. Okay, so and almost got the information entropy as much similar, and then a quite minor variation in green and blue channels. And another important parameter is key space analysis. In cryptography, large key space, the more secure algorithm, and also the stronger ability to resist brute force attacks. Brute force attack, see, the kind of attacks. Suppose I have a 2-bit code. With how many attacks I can crack the 2-bit code? How many attacks are enough? A binary 2-bit binary number is there. How many attacks are required to okay, to get the decryption of that? Just 4 attempts. How can you say 4 attempts? 0 0 0 1 0 1 1. So just the 4 attacks are enough, right, to crack a 2-bit binary code. So, but for images of such size, okay, it requires a large, for a n-bit binary. How many attacks are required? N-bit binary, 2 power n attacks. Suppose 10-bit binary is there. How many attacks are required? 2 power 10. That means 1024. As the size of the this size is increasing, it becomes quite difficult. More and more number of attacks. For example, 1000, 2 power 1000 number of attacks, like that. The key space of logistic, lossy, and the tent maps of the algorithms proposed by authors, they are listed in table. The parameter setting and the initial value of each chaotic map require 32 bits, and hence the key space of the proposed algorithm is 2256. Therefore, this key is effective key against the brute force attack, since this is greater than 2100. This is greater than 2100, and by comparison, the key space of the proposed designs by the authors are better than most algorithm key space that are listed, which are shown in the table 10. So let us look at that table 10. We'll see that table 10 also. We'll look at that key space analysis. 2 power 256. The key space of the proposed algorithm is not 2256. It is 2 power. It's a typographic mistake. This is 2 exponential 256. As I said, 2 power n. It is 2 power 256. It's a typographic mistake which I am showing in the key space. I have highlighted that. Please do observe, and you need to correct that. Here is the key space that is given. 2 power 32 power 2 is 2 power 64, and then 2 power 32 power 4, it is 2 power 128. The key space is going to play an important role. And there is another parameter called differential attack analysis. The attackers try to find the relation between the plain image and the encrypted image by making infinitely small change between two identical plain images. For example, change only 1 pixel for two images and observe the corresponding ciphered image. Therefore, Chen and other, they use two measurements: number of pixels, change rate, and unified average changing intensity for this purpose, which measures the average intensity of differences between the two images. The NCPR means number of pixel change rate, and UACI is the unified average changing intensity, which is given by this NCPR is given by this equation, and UACI is also given by the equation, where in both the equations we use W and H. They are width and height of the ciphered image. C1 is the encrypted image, and if 1 pixel is changed of C1 in random, the ciphered image C2 is obtained. C2 is the ciphered image after 1 pixel change from C1. And Dij, we are defining that Dij is equal to 0 if C1 I of j is same as C2 of ij is 1 otherwise. And the table 11 and 12, they shows the UACI, which is nothing but unified average changing intensity values, comparison between different channels. And tables 13 and 14, they gives NPCR test comparison. This is a UACI test comparison, and NPCR test comparison is shown here. So the sizes of the images were varied. So you got various tables. So why you got three tables? Why three tables is, one is for the image size of 256 by 256, other for image size of 512 by 512, and 1024 by 1024. So the generator instruction in system generator block can be used to obtain the VHDL code. See, you can obtain the beauty of this system generator is that you can get even the VHDL code also for all pseudo random bit generation. And the others has proposed the systems, and they are designed using the Xilinx evolution board with number. The number is given there. The device utilization summary for the proposal. See, each FPGA has the resources. What are the resources inside the FPGA is IOBs, input output blocks, input output buffers, slices, slice registers, LUTs, lookup tables, BUFGs, multiplexers, and also maximum clock frequency, peak memory usage. So all these are important, which are tabulated here. What slice registers? You observe that available slice registers are 54,576, and FPLOM-BRG used only 51 number of slice registers. 98 slice registers are used by FPLM-PRBG, that is a Logi map. You have three chaotic maps. Okay, the three chaotic maps are shown here. TM is a 10th map, is have used almost 10th map, and the first chaotic map has used the same number of resources. But for pseudo random bit generation, you observe 168 and 102. Now the question is, why this comparison table and resource utilization? What is the significance of this tabular form? Now, suppose you implemented this Xilinx Spartan FPGA, and you implemented these pseudo random bit generators. Now, you observe that hardly you are utilizing only the percentage utilization. If you calculate, out of 54,576 available slice registers, you are using hardly the highest number of slice registers is 168 only. That means the same FPGA is used even for higher size pseudo random bit generators. That's what the understanding you can get from this device utilization summary. Number of lookup tables 27,288 are available in your FPGA, whereas your particular system is utilizing only 238. That means that even you can go and implement the high sized pseudo random bit generators, making use of the same FPGA. So you need not change your FPGA even for high sized pseudo random bit generator. That is what you can understand this from this device utilization summary. Are you able to understand this? The throughput of the system is the amount of bits for each second and is defined as throughput is equal to maximum F maximum multiplied with 8, and where F maximum is the maximum allowed clock frequency. So from the tabular form, it can be seen that the highest complexity with low maximum for both frequency and highest complexity is, which is having highest complexity is FPCCM PRBG. FPCCM PRBG is having highest complexity. That's what you can observe. It's having highest complexity for both frequency and throughput. So observe frequency and throughput parameters of FPCCM PRBG. Observe the maximum clock frequency is 10.292, whereas for all other it is almost double the clock frequency. If it comes to FPTM PRBG, it is 46.712. That is almost 4 times that of FPCCM BRG. That is what is said here. From this table, it can be seen that highest complexity with low maximum for both frequency and throughput is for this, while the light PRBG system is FPTM PRBG with highest maximum both frequency and throughput. Frequency and throughput are highest, right? Frequency and throughput both are highest. See, these are correlated, throughput and these are both are high. Because you have an equation in dynamic power related equation, P dynamic is equal to half CV square F. If the frequency is high, almost the power consumption is also high. Okay, but we are not talking about this thing. Throughput is throughput and frequency relation should be checked. The throughput result make the proposed system safety because it is suitable for obtaining the needs of secure and robust encryption cryptographic systems. So you can see the image encryption system that is shown in figure 16. So you may use a desktop system to which you can observe that the Xilinx FPGA kit got connected through JTAG cable, JTAG port, when JTAG co-simulation link is established. Then the serial samples output from the FPGA device is sent back to the PC and test the picture using Simulink or MATLAB viewer. This is a real-time implementation that can be done. So in this paper, with due acknowledgement to the original authors, Hassan and Amir, a color image encryption algorithm using chaotic map based stream cipher is implemented using Xilinx system generator technique. The chaotic maps are converted to fixed point format, and these maps are used either as alone or combined in XOR or cascaded mode. The security analysis can be done making use of different parameters like histogram, correlation coefficient, entropy, and key space analysis for different sizes. Also, the authors has proposed a system with good key space, which is sensitive to slight changes. The synthesis results show that its maximum frequency is about 23.356 megahertz with throughput of 186.84 megabits per second, which is suitable for a nowadays for the secure system. And the others has proposed a system which is able to use multiple requests to increase the throughput for high definition at the expense of hardware complexity. Finally, a real-time system was done by the authors and tested using hardware co-simulation via FPGA Xilinx kit. So this concludes, and with due acknowledgements to the original authors of this particular research paper titled FPGA hardware co-simulation or image encryption using stream cipher based on chaotic maps. So that's what from my side to share with you. So any questions regarding this?
Thank you, sir. Thank you so much. I request the participants. I request the participants if to express their doubts, if they have any doubts.
So Hemlata madam and Grishma madam, that's all from my side. I once again express my sincere gratitude for giving me this opportunity to share my knowledge. Thank you.
Thank you, sir. Thank you from our side also.
Shall we conclude?
Yes, sir. You can conclude, sir.
Yeah.
I think you can leave your. We have your mail ID. If there are any doubts, because this is a trending topic that you're saying, sir, and most of students, actually not from the side of the staff, but most of the students are wanting, from this field of interest, sir. So I would I'll take your mail ID, sir, so that whenever we get the doubts, I think we can express our doubts through the mail ID. Is it okay, sir, for you?
Yeah, definitely. I'll be happy to.
Because FPGA, and we have a lot
I'll
of
be happy
papers.
to
We
share.
also want an elaborated, this thing's elaborated, this thing, on this subject also, sir. So we would like to interact with you through the mail ID. So I'll definitely take the mail ID, sir. So really, it's a great session, sir.
Yes.
Thank you, and thank you so much for accepting our invitation, and wonderful session. And now we can conclude, sir. Thanks once again from the bottom of our hearts.
Yeah, once again, I have to thank all the participants and the organizers of this workshop and giving me this opportunity to share my knowledge. I thank the head of the department, who is a good friend of me, and also I thank Hemlata madam, Grishma madam, and all the faculty members of CRED Engineering College and the participants. Once again, thank you for your active participation.
Thank you, sir. Thank you so much.
Thank you, sir. Thank you very much, sir.
Yeah.
Hemlata madam, would you like to speak?
Thank you, sir. Myself is Hemlata. Thank you very much, sir, for your great explanation and practical orientation, sir. We are learned so many things from this one, sir, by using system generator, how we can use that one, sir, some idea we will we get, sir. Thank you, sir. Thank you very much.
Thank you.
So participants, so this is the end of the morning session of 4-day of FTP. And the second session starts in the afternoon at by 2 p.m. So our afternoon session guest will be Rahim Ahmed sir, which will be continued. The session of Tuesday afternoon session will be continued. Wednesday afternoon session will be continued today afternoon. So this is the most awaiting session, and we request all the participants to join sharp by 2 o'clock for the Rafi Ahmed sir. Thank you, and thank you once again for everyone.